translation of the examples that I'm giving. And please interrupt all the time.
Can we interrupt again before the talk? So one thing I forgot to say is about use of fonts. So somehow, to me, it's disturbed when people use the font. So I don't mind iPads or computers, and even phone if you check something related, like you check a definition or a theorem that's related to the talk, but don't look at email and answer it, because then it's impossible to stay focused. I know it myself. Sometimes in the past, sometimes it was a talk. At some point, okay, I know this stuff, I can check my email, then if you check the email, you cannot go back to understand. So let's respect the midrasha by avoiding font. If someone calls you and you have to answer, you can go out. Okay. Go on.
Okay, so Bass-Serre here. Okay, so the only thing we'll do before the examples is just let me tell you what's the goal of this thing is we take groups that are acting on trees, but it may be groups that you did not think that they are related to trees in any way. For example, the free group, or for example, SL2Z, just groups, and we will observe their action on the tree, and by this we will analyze them and their properties. So that's the idea of Bass-Serre, and there is some kind of, you can go in both directions. You can take you can take a subgroup, then understand its action on the tree, and go back and realize its structure, or you can take a group with some structure, and by this structure you can construct a tree on which this group will act. Okay, but so this was like 30 seconds on Bass-Serre theory, but now let's just view examples. Okay, so example one. So you all know the free group. So let's take gamma, the free group on R generators. So we know that we can realize this gamma as a fundamental group, right? So the gamma is a fundamental group of what?
Okay.
Just a bouquet of circles, right? So we have R circles, and FR is the fundamental group of this thing. So during the talk, I'm gonna abuse notation, and now when I write a fundamental group, I mean fundamental group as you know, but in like 10 minutes, we will generalize this to something which is called fundamental group of a graph of groups. So this one is a graph, but we will also talk about graphs of groups. And then pi 1 will be the fundamental group of this graph of groups, which is something sometimes larger. But here in this context, it is still just the fundamental group. So we can realize this gamma as pi 1 of this. And then how does the universal cover look like? So the universal cover of this pair is a tree, right? Which will be 2R regular. So this is the universal cover, and we know that the group gamma acts on the universal cover by deck transformation, right? So we know that gamma acts on this X by deck transformations. Okay, let me just, we'll draw it once just to be sure that we are on the same, we are talking about the same thing. So if our bouquet of circles is just, if it's the free group of two generators, then we have the one loop, we have A and B. Then the universal cover will be the 4 regular tree, and maybe this vertex I lift it to this V. And each vertex, all vertices look the same. So now what is the action of my group, of the free group on this tree? So in my context, I'm thinking of this group as a group acting on the tree. This is the tree. And what is the action of the group on the tree? So for example, if I take the word, if I take here the word a b square, then how does it act? So I'm starting by, I'm lifting v to here, this is v tilde, and then I'm going toward a, this is the edge a, and then I'm going twice with b. Okay, I'm getting here. So this will be the image of v tilde under the word a b square. Okay, so I have that my group is acting on the tree by that transformation, and I'm realizing gamma as a subgroup. So since it acts on the tree, then you can think of gamma. So to summarize, I have that gamma is a subgroup of the automorphism group of the tree, because it acts on the tree. It acts faithfully, so it really is a subgroup. What else can we say? That this thing, we can think of gamma as pi 1 of, so now instead of writing bouquet of circles, let me state it as gamma mod x. So right, if you take the 3x and the action of gamma, these circles are just the quotient graph. So in my case, gamma is the fundamental group of the quotient of x by gamma. And this is the case we will always want to get. We will always want to understand groups acting on trees, or groups which are a subgroup of the automorphisms of a tree, as fundamental groups of some graphs. What is the graph? The graph is the quotient graph of the tree by the action of the tree. Okay. So, and in the next hours we will work with this on both directions. We will sometimes prepare a graph, then using it to construct a group, and sometimes we will take a group and see what is the graph of which it is a fundamental group. And here just a remark. Here we had that the action is free, so we had no stabilizers there. So for every vertex v in the tree, the stabilizer of my subgroup gamma, the stabilizer of the vertex x was trivial. This notation?
Over there, the pi 1 of x mod gamma.
Pi 1 is the fundamental group. Here, you mean this?
The x mod gamma itself.
What is
X mod gamma itself. So it's a good question. So when I write it like that, I mean just the graph. So x is a graph, and when you mod it by the group action, so you know few vertices. So it's the graph of orbits, but of both edges and vertices. Each vertex here is an orbit of vertices, and each edge is an orbit of edges.
So it's the orbit space of the gamma action on the tree, but you should realize that there is a natural graph structure on the orbit space.
Since the gamma was really inside the automorphism, so if two vertices were neighbors in x, then they will still be neighbors in the quotient. Okay. So thus it gets really a structure of the graph. Okay, but it's a good question because sometimes I will. Okay, so when I denote it only like this, it's really the quotient space. Soon we will have a more sophisticated notation. So here in this case, it is also pi 1 of what I call gamma double slash x. So what is gamma double slash x? Gamma double slash x is a graph, and a grouping. So A is a graph, it's just the graph gamma mod x. But then to each vertex, I also glue a group. What will be the group? The stabilizer. Okay, but we'll do this soon. But here, since we have no stabilizers, so really these two objects look the same.
Is that the standard notation? The double
Yeah,
slash?
yeah, it's a standard notation. It's
On
so
its
all
back.
this can be found in the book about trees of Bass-Serre, and they use this notation. And yeah. Okay, so this was the first example. Yes. Ask me first.
So maybe a word about this piece of notation. I mean, first of all, it's backslash. So it's double backslash or back double slash. I'm not sure.
Ah, this is.
But this double whatever used usually to denote categorical quotients. In algebraic geometry, when you have a group acting on or an equivalence relation on a certain variety, then you can take the space of orbits, but this is not a variety itself. So to distinguish between, but maybe there is a quotient variety in the sense of algebraic geometry, and this would be denoted by x double slash whatever. I mean, yeah, and it distinguishes this from the standard orbit space. And if you vary your category, you can have different uses of the same thing. In ergodic theory, just to mention, if gamma acts on X, and this is the measure space, we denote by X double mod gamma the space of ergodic components. So the measured space consisting of ergodic pieces in X. Okay.
So is double slash usually Hausdorff?
Sorry?
Is double slash usually Hausdorff? It's quotient in general, it's not.
I
It's double slash usually Hausdorff, it's quotient in general, it's not Hausdorff.
I would say that if you look at, okay, there is no canonical Hausdorffification of a topological quotient. So I would assume that if you look at just actions of gamma on topological space by homeos, then the double slash should be denoted the space of orbit made T0 or something like. I mean, here it's just a piece of notation, but just because it was asked, there is a general use of this thing.
So after we discuss it, I can erase it because I hate when when the board is divided in such a like leave it like that.
Another natural example is the character variety. When you look at all the representation of a given group, so gamma is a finite generated group and G is an algebraic group, and you look at home gamma G, that's an algebraic variety because gamma is generated by, let's say, n elements, so you can embed home gamma G in G to the n. If gamma is the free group, it's just isomorphic to G to the n non-canonically, but it depends on selecting generating set. If gamma is not free group, then you add the relation. The relation are algebraic polynomial on this on G to the n, that the zero of them, or when they equals to the identity, that's the polynomial defining the representation variety. Now, usually people don't look at, in many cases, you don't look at the representation variety, but on the character variety, which you let G, the group, the algebraic group, act by conjugation. You identify the representation if they're conjugate. And then when you divide by this action by conjugation, it's not an algebraic variety anymore. But there is an associated algebraic variety, and this is denoted by double slash. And the algebraic variety is defined by the polynomial or the regular function, which are invariant under the adjoint action, conjugation action.
This is exactly an instance of this categorical quotient
Yes.
in algebraic geometry that I was
Exactly. So, and in this case, it's not Hausdorff, but it's the Ritzky, the topology, the Ritzky topology.
I want to ask about when you said that home gamma G, you can embed it into G to the R. Does so it's a bijection, but there is a topology on both of them that is preserved. Is there?
And there is Okay, and we don't discuss the character variety here, but yes, there is the natural topology of home gamma G is I mean, if G is, let's say, a Lie group or a topological group, then the natural is the pointwise convergence topology, and then it's coincide with this. But in the case that I discussed, it's the Zariski topology.
Yeah.
Yes.
And there.
The Zariski topology on G to the n induce the Zariski topology on home gamma G.
So we didn't have topology to begin with on home, or
Depends if you have a topology on G or not.
Yeah, I mean,
suppose it's an algebraic group. Sorry to.
okay, let's
Okay.
discuss it. It's not. It's just we want to demonstrate the notation.
It's
but
on Bass theory
Yeah.
and double slash notation.
Okay, let's come back to.
Okay, second example. That is the group PSL2R, PSL2Z. Okay, so recall just we already discussed it in the Midrash a few times, but just let me write the main things that we know that SL2R acts on H2 by Mobius transformations. So that is we send a matrix sends Z to AZ plus B, CZ plus D. And we know, that the action is transitive. If you want, you can send I everywhere. So by this matrix, for example, this product of matrices can send I to x plus yi, so we know that I gets everywhere, it is transitive. The stabilizer is of the point I is the compact group SO2. Okay, so this is the action on the hyperbolic plane, and we know that inside we have the group SL2Z, inside SL2R, let's call it gamma, and we know that this group has a fundamental domain which is this. So this is the set of all Z with norm larger or equal, greater or equal to 1, and the real part lower than half, or most half. And the fact it's a fundamental domain, it means that every point in the hyperbolic plane has a unique point inside this to which it can be sent by SL2Z. And following Ariel, which brought us many pictures, I also
For almost every point, only.
right, except the points on the boundary, which this point, for example, can be sent to this point and similar to the rest of the line. But for the interior, it's really a fundamental domain. But okay, we will just use now the surroundings. Okay, so this is the picture. So what you see here is I2 is the fundamental domain, and what you see is how the hyperbolic plane is divided to copies, to translations of this fundamental domain by the action of SL2Z. So I don't know if you can see the T and the S, but it is known that SL2Z is generated by two specific matrices, T and S. And you can really see like which word in these two letters translates this fundamental domain.
You can write them specifically.
נכון.
Yes.
So help me not to get confused. So T is
One word.
this, right? And then S is what? Is 1 minus
Yeah.
1. This. Okay. So this is T and S, and okay. So let's add it. So T and S. So T and S generate gamma. Okay, so these are all the translations. I care about a specific edge in the boundary of this image, which will be. I will also draw it on the board, but this image is so nice. So I care about this specific edge. So this vertex, I will call it Q, and this vertex I will call P, and this edge will be E. And what I'm going to do is to construct a tree. Okay, מעולה. I'm going to construct a tree by viewing all the translations of this edge by the group SL2Z. So this tree will actually be supported on the lines that you see, because it's on the boundary of this fundamental domain. So it will stay on the boundary of these copies. Okay, and we will consider this tree, and we will observe the action of SL2Z on this tree. And then we will decompose SL2Z as an amalgamated product using this action. Okay, so let me write the details. So consider the following edge. So my edge is a Q. Q will be just I. So it's this vertex here in the middle, or here. And my P will be half plus square root of 3 divided by 2I. So it's this point here. This point here. And the edge between them I call E. So the edge, I mean the boundary of the fundamental domain, I call it E. Okay, so this is my edge, and this will be kind of the fundamental domain of the tree under its action, under the action of SL2C. So denote by X. X will be the union of all translations of this edge by the group SL2 or PSL2Z. Okay, I didn't write it here, but inside SL2Z we know that we have the element -1. So maybe let me add it here. We know that the element -1 sends Z to Z, so it's just the ID. So it's just the ID, and therefore we know that we have an action of PSL2Z. So this is the kernel of the action of SL2Z, so we have an action of PSL2Z on the hyperbolic.
So PSL is going to preserve the edge orientation.
Right, it's going to preserve the edge orientation. It's true. So actually what you're saying, so why is it going to preserve the edge orientation? Because I cannot be moved to P. So it cannot invert the edge, because it cannot switch the points Q and
But just not to get confused, PSL2Z is not an index 2 subgroup in SL2Z. It's a quotient. And SL2Z acts, but -1 is in the kernel, so PSL2Z acts actually. So also SL2 preserved the orientation.
now I see what you're, okay, now I understand what you meant. So PSL2Z is both a quotient of order 2 of SL2Z and a subgroup of index 2 inside the, inside.
PGL2.
Right, if you want all the more. Okay, so about
It also, no, PGL2 also doesn't.
But if you allow also inverting the edge, then you will get a larger group. Okay, that's.
Once again, how do you prove there is no inversion in the graph?
Okay, you can check the numbers and then see if there was an inversion. Okay, so we will write the details of how the action looks like. But if there was an inversion, so in particular you could invert E.
Okay.
Because the action is transitive on edges. So if you could invert, or we'll write it down, but if you could invert, maybe we don't need to write it down, because by the definition of X as being all translations, then you get that the action is transitive on edges.
Yeah.
And then if you could invert some edge, then you could invert every edge. And in particular, you could invert this, and then you should just write the calculation. You should write whether it is possible that AZ plus, AI plus B divided by CI plus D can be equal half plus this for ABCD integers with determinant 1, and you will see that it cannot happen.
But there is no
I guess
argument.
also you could just maybe observe it here in a way, right? If you will take a very small neighborhood of I, it cannot, it is in the middle of the fundamental domain, it cannot.
But there is no argument which lie on the theory, on the whole theory on H2. You have to consider the graph and prove that there is no inversion. There is no general.
I don't know of a general way of stating it, but it's a pretty easy calculation
yes,
because
yes,
it's only
in this form,
integers
yes,
that
it
need to
is.
reject.
It's because it's a fundamental domain. We know that the P and Q aren't the same.
Right, but there is
but
the
there's a
problem with
boundary.
the boundary that Sahik said that on the boundary it's not really one to
But
one,
if you-
but it is true that this point is similar to this and this is to this, but this point is not similar to this. So it is you can convince yourself by looking at the fundamental domain shape that it cannot, this one cannot be translated here.
If you do the construction that I gave of this fundamental domain, you see exactly which points there are.
Right, so yeah.
These two.
רצית גם
I just want to say that the notion fundamental domain is overused. Sometimes we use it to a precise fundamental domain which represents each orbit exactly once. But sometimes by abuse of notation we also include boundaries of such a thing. And so this picture, I mean, you did say it, but just
I
want
think
to
that if
emphasize,
you-
is not
Yeah.
an actual fundamental domain.
But am I correct that if I, erase only the this side of the boundary, then it is
No,
a one-to-one
because-
fundamental domain?
Because there is
Ah.
a stabilizer. There is a stabilizer of I, and there is which is order 2 group, and there is a stabilizer of this, which is order 3
Yeah,
group.
but it does represent all
I think
orbits.
it's all- it
yeah,
represents
yeah, okay.
I mean, it doesn't
one-to-one.
encode all
Yeah.
information, but it is a strictly
Yeah.
fundamental domain.
So I think if we just erase the boundary, the right side of the boundary, then we really get a fundamental domain, and then this really maybe shows that this point and this point cannot be sent to each other.
But-
Because this already belongs to this copy of the fundamental domain. This point already belongs here, and this point belongs here.
If you S is the map Z goes to -1 over Z, which identifies
If
this
S
part
is
of
the
the
map,
circle with the other one.
Z goes to 1 over Z, yeah,
-1 over Z.
minus 1 over Z.
And it identifies this little part of the circle with the other part, and
This part with this part.
yes,
right,
and
right,
flips
right,
the orientation
right,
and
right.
T does left and right. And this is how
So
you
it flips the orientation, but this point is stabilized, right? And this goes here. Am I- Yeah.
Yes.
So it does not flip the edge on the sense that.
No.
Yeah. Okay, but you're correct. So what you're saying is really like how to begin constructing the tree, right? That's a translation of this edge, and we can keep doing, translating it around. And you should trust me that indeed what you get is connected, and it has no circles, and it is indeed a tree. And I also printed a picture of that. So this is the tree. So I don't know, not the קווים מקווקווים, but only the real lines. Not the real lines, but only the lines are parts of the trees, and you see that maybe you see, maybe you don't see that P and Q are colored differently. So Q is the blue dots and P is the white dots, and they cannot switch.
Can
Maybe you
you
can
pass
pass
it
it
around?
around.
Enjoy the both. Okay.
But maybe just if we discuss the stabilizer, so if you look at this picture, you see that the stabilizer of P is exactly S. What S does is take this here and like that. So S and 1 is the stabilizer here, and the stabilizer of this point is TS and ST inverse.
So let me
So
write
it's
it
a
down.
order 3.
So let me write it down. So X is the union of all translations, and fact. It's a fact that X is a tree. And now let me write what Tzachi just said about the stabilizers. So stabilizer of Q, so Q is actually I. You can calculate it. It comes out that it is the subgroup generated by S. Okay, so that is the stabilizer inside. Okay, inside PSL to Z. So inside PSL to Z, so you see this matrix squared, it gives you -1, which is already trivial if we are in PSL to Z. So this group is actually Z mod 2Z. And you could also calculate the stabilizer of the point P. Okay, to get something generated by, אתה זוכר את המטריצה המדויקת? Which is what? Which is
-1, 1, -1, 0.
Okay, let's hope that this is the matrix. And this matrix, when it is cubed, then it gives you -ID, which means that inside PSL2 this matrix is of order 3. So this group is actually Z mod 3Z. If you consider the tree, so maybe I will draw just, so this is Q and P, and this is the fundamental domain, but this is not part of the tree.
And you didn't tell us for the extra edges.
I will not draw the extra edges, I will עושה לעצמי חיים קלים. Just a small part of it, so you see that the stabilizer of Q is of order 2, and what does it do? Exactly flips this edge and this edge, so it stabilizes Q but moves this here. This is the element that Manuel just mentioned, moving this to
In
here.
fact, it flips all the right-hand subtree
Right,
and the
and
left-hand
after flipping the edge, it's an automorphism of the tree, so it takes all the part of this tree, moving it there. And the stabilizer of P, which is of order 3, is exactly, rotating these 3 edges, like that. So it's of order 3, and also it's, all this part of the tree is going here, this one is going here, this one is going here.
So just to make the remark that for our Euclidean minds, when the tree is drawn this way, the symmetry Q is symmetry at Q of the stabilizer is very, very easy to imagine. It's just a mirror symmetry. But the symmetry P, which is rotation, is slightly more complicated to imagine.
And this is the axis, right? That's the y. Okay, so this is the and the thing we just said about the rotation tells us that observe that each stabilizer the stabilizer of vertex V acts transitively on the edges going out from V. For both P and Q and every vertex here. And what else we need to observe? I think that's it. Okay, and in general, the group, and in general, PSL2Z acts transitively on edges. Okay. On edges, on the edges. Okay, now what is the hidden claim here? What is like the punchline? What do we want to say? We want to observe that our group PSL2Z is actually the amalgamated product of Z mod 2Z times Z mod 3Z. Or in other words, it's just the amalgamated product of the stabilizer inside the group of Q with the stabilizer inside the group of P. This is the stabilizer inside PSL2Z and the stabilizer inside PSL2Z. And this is the, נכון, I did, okay, נכון. Here it's the free product, And after we are done, we will also observe that if we consider just SL2Z, then it will be the amalgamated product along Z mod 2Z, which is the common subgroup of both stabilizers.
So the graph that you've
Seems
drawn
order.
is dual to the Cayley graph with PSL2. You just replaced every
it-
triangle
okay.
with a white
Why?
box.
Is it? I want to say that it cannot be like the Cayley graph because it has
dual.
stabilizer, but it is dual to the.
If you
Maybe
replace
you
all
are right.
the white vertices with triangles.
Maybe you are right. Maybe you are right. Yeah, and then it's order 3 kind of thing. It makes sense. I didn't think about it, but yeah, but you're correct, I guess. Okay, and these ones you also switch by small. What does it need to be? The loop or something?
You just
No.
remove the black and you replace the white by triangles and you get the Cayley.
Okay. I believe you are right. You are correct. Okay, so this is the claim. Okay, one. So we need to observe three things. The first is super. Okay, clearly we have that what is generated by the stabilizers is contained in SL2Z, right? In PSL2Z, that's clear because both are subgroups of PSL2Z. Second, we need to observe the other inclusion. We need to observe that PSL2Z, I'm going to call it gamma just. We need to observe that gamma is generated by these stabilizers. And then after we convince ourselves so this we already know. We need to convince ourselves in this. And next, we need to convince ourselves that these two has no relations. So the product between them is indeed free. So it means that if I take an alternating word having a letter of here, a letter of here, a letter of here, then it cannot be trivial. So the third thing is to observe that what is generated by these two things is indeed free. Okay, so let's do it. Let's prove it by looking at the picture. So I'm gonna 1, 2, and 3. So let's prove 2. Okay, so give me an element in gamma, and I want to show I can generate it by the stabilizers. So since and let be non-trivial. So if I have a non-trivial element, it definitely translates E. Why I know for sure it translates E? Because in the action on the hyperbolic plane, if you stabilize 3 points, you already stabilize everything. So in particular, if you stabilize an entire edge, then you must be trivial. So I know that if this element is non-trivial, then I know that there exists some edge y. So I know that E, this is our main edge E. I know that E is translated somewhere, or in other words, I know that there is some edge translated to what did I want to say? Translated to the edge E. I will, okay, now we construct a word in the stabilizers. In the stabilizers, a word in the a word, how will we call it? A word F in the stabilizers such that F translates gamma to E, translates Y to E. So I want to make the element gamma. So in order to make the element gamma, I want to take this edge Y that I got and send it back to E. So how am I going to do it? Using only stabilizers. So observe that now y is pretty far from E. Okay, but if I take the stabilizer of Q and I will translate E here, I will take E and move it here, then in particular, am I saying the right thing? No, I wanna, if I act with the stabilizer of P, and I will send this edge into this edge, in particular what will happen is that Y will get closer to E. Right now the distance of Y and E is 1, 2, 3, 4. If I will act with the stabilizer of P and move this edge into this edge, then Y will move somewhere, for example here. This will be, I will call it T1 of Y. This is Y and this is T1 of Y. So by acting with the stabilizer of P, I can take Y and bring it closer to E.
Let me say it in a shorter way.
Say it in a shorter way, please.
There is a general phenomena here that happens in many situations. When you have a connected space, like here is the tree, and you have a group that acts properly on it. So, like in this case, the group generated by. So you have a connected space, and then you have inside a connected piece, like which will be the fundamental domain, and then suppose that a compact and connected piece, like this edge is compact and connected, and with P and Q you can cover all the environment, all the neighborhood of this edge. So then, in general, when you have this situation, P and Q will generate the full group.
So like the stabilizer of P and the
because
stabilizer.
the group, you see what happens to this edge under the group generated by P and Q. So it covered the surrounding of it and the surrounding of everything. So you get something which is both open, because everything you cover the neighborhood of it, but it's both closed, because you start with a compact piece and the auction is proper, so it's open and closed in a connected space, so it must be everything. And this is a general phenomenon, and in many cases, for instance, Weil used it in this very simple and elegant but smart, clever proof. He was the first one to prove that co-compact lattices in Lie groups are finitely generated. And this is exactly this is the proof he used. He took connected fundamental domain and argued on that.
But here you said that the edges go to surrounding edges.
So look at this edge and look at the group generated by P and Q. Just by, and I claim that this group acts transitively on the tree. Okay? Because with P and Q I can cover the surrounding of this edge.
To be precise, maybe take all elements in the big group that takes the piece in a way that it intersects itself.
Yeah.
That's a subset, and you take the group generated by this subset.
But this is exactly P and Q.
Yeah,
P and Q and Q and P squared.
But for the general claim.
Yeah. For the general claim, I take everything that I could take a connected compact piece, and I look at all the elements the finitely many elements that take it to something that intersects it. In that case, it's just Q, P, and P squared.
Which is in a general space, not a graph.
In general, yeah, you need a connected space, and you need the group to act properly, and then you can argue like that. And but this argument is also applies to totally disconnected group, because totally disconnected group, you don't associate the action on themselves, but the action on some tree or a Cayley-Abel graph or a Ritz complex. You can always associate a connected.
So let me state and leave it as an exercise. What something? Okay.
Everybody has this picture in his mind.
X connected. G acts on X properly. So part of the exercise is to introduce yourself to the notions that appear here coming to join. important. Maybe sometimes we introduce it in the Midrash, but I don't want to make this.
Let's just be careful and let X be connected and proper. Did you follow? Let's assume. You want to do?
I don't think.
If X is not proper, then you can argue what means
K
proper.
inside X. Compact. Oh, you need it to be open. Oh, now I'm confused.
What do I want?
Maybe open by compact?
Open.
Open.
Compact
No, open.
with,
Open.
yeah.
Just open.
No?
Now I'm here. Okay, it's like.
You want me to say?
So, I'm not sure. Now I'm confused about the exact
So, let's say that K is the K equals to the closure of X and K. K is compact and equals to the closure of X and K.
And now define S in G to be all the G's such that GK intersect K is non-trivial. But yeah.
We need it to be properly discontinuous.
The action is proper. That's what we mean by proper.
Yeah. If you know these notions for if G was discrete, properness is proper discontinuous. I mean what's known as proper discontinuous. Then the group generated by S inside G is all of G. So.
Okay, does it count like I did it too late? Okay, let me because I said to myself in the morning, even if I don't manage even 1/4 of the lecture, then I will give the break on time. But okay, so
did you manage 1/4?
Yeah, even I would say 2/3 of the first part. But let me just summarize. Assume we proved all these and it's all true. So we really have that PSL2Z decomposes as this product of stabilizers. And I just want to say the word graph of groups before we go to the break, and then you can hear it again after we are back from the break. So I also want to think in this context of gamma, PSL2Z, being pi 1 of a graph. What is the graph that should be written here? The graph that should be written here is gamma mod x. So what is in this context gamma mod x? So x is this tree, and gamma mod x, so it's the space of orbits. So we saw that this E is really, that's the fundamental domain of the thing. So this is actually this vertex Q, this edge E, and this vertex P here. But it is double slash here, so it means that now it's not just a graph, it's a graph of groups. What does it mean, a graph of groups? It means that to each vertex I attach a group. What will be the group? The stabilizer of the vertex in the group. So here on this Q there is like a second layer, not only the graph. So I have the graph, and to the graph I attach groups. Here I attach the stabilizer of Q. To the edge I attach the stabilizer of the edge, which in this case is trivial, but it can be non-trivial sometimes. And here I attach the stabilizer of P. And roughly speaking, what does it mean to be pi 1 of such a thing? So if I took the pi 1 of this graph as a graph, this would just be trivial, right? Because there are no loops in this interval. But a pi 1 of a graph of groups means that whenever you travel in a vertex, you take a base point, say this was your base point, and then you start traveling. and you're traveling, and whenever you meet a vertex to which there is a group attached, you are allowed also to take a letter from this group. So how will a typical element in this pi1 look like? You start here, you take some p1. So how does an element G in pi1 look like? You start here, for example, in the base point, and you take some p1, p1 which is an element in the group gamma p. Then you keep going and you got to Q, then you're allowed to choose some element from the group Q. So let's call it Q2, which is in gamma Q. And then maybe you kept on walking, you went like that, then you came back, you arrived at P, then you're allowed to take an element from P. And this can be also done on larger graphs. In this graph, the only loops that you can do is go here, take an element, go back, take an element, go here, take an element, go back, take an element, and so on. But in general, graphs of groups will be taking a graph, attach a groups, and consider loops with letters from the groups on the way. So this will be a typical element here, and in general it's a loop with letters. Okay, so that's it. So next.
So maybe just say but it's not. I mean, suppose you have a graph, and in each vertex you have the trivial group. So when you do a loop, you take the trivial elements everywhere. But
you are right. So I was lying a little bit, because in your graph, whenever you will also have a loop in your graph, going around the loop will also count as doing something. So just let me. So we saw just two examples. So, but in general, when you have a graph of groups, it looks like, let's say, you have P here, you have Q, here you have gamma P attached, here you have gamma E attached, gamma Q attached, and you may also have a loop here. So the elements will look like, say I was here, so I took P1, then I went here, I took some Q1, Q2, then if I did a loop, this will also count as doing something. So maybe the loop, we call each loop gets a letter. So the loop is, say, Y. So then I have here a letter Y. Then if I came back, then I can take another letter from Q. Let's call it Q3. And then I went back, I took a letter from P. So this will be P4. So that's a typical element which stands for the loop I draw. And you could also just, do a loop, then you will just get Y or Y square, or depends on how many loops you did. If it's the free group, for example, the stabilizer was trivial, so here you had the trivial group, but you have these loops. So this is Y1, Y2, and then you see that the fundamental group of this, whenever you visit here, you just take the trivial element, because there is no group attached here. But whenever you take a loop, you really count, Y1, then I did Y2, then maybe I did Y1 again, and Y again, and so on.
Well, this loop you can actually add to gamma Q, but formally somehow. But what happens if you don't have loops? You just have a graph, but not a tree?
If you don't have loops, and all, if you have no loops and all groups all stabilizers are really trivial, then you will really get the trivial group.
But
the graph of groups of such a thing, where all groups are trivial here.
No, but the graph is not. But the graph is not a tree. Suppose you have a triangle. Yes.
Okay, so when I'm thinking of this, I'm taking a spanning tree, then I squeeze along the spanning tree. Okay, so there is other things to say here, but that's the graph.
What was the punchline in the spanning tree thing?
So this,
what do you do to
you
this?
don't take a graph of group at that. You first take a spanning tree, and then you will.
What is a spanning tree?
So the truth is that when you have a graph, when you really have a graph of groups, so it may look like that. You have G1 here and G2, and you have groups attached to all vertices. And then actually the way to construct, so what is the pi1 of this thing? So you take a spanning tree. Spanning tree is a tree that touches all vertices.
Isn't this the part that you wanted to explain after the break?
No, after the break we will leave this and do something else. So I will say it in one word. So you take a spanning tree. All edges along the spanning tree don't get letters. all edges which are out of the spanning tree, in this case it's only this, get letters, for example this will be y1. And then when you take a loop, you choose a base point. If you travel along these kind of edges, you need nothing to say. You just take an element from G3, take an element from G4. Then when you cross here, you really write y1,
Okay.
and so on.
Okay.
Yeah.
And this is a spanning tree.
And this is a spanning tree. Yeah. Okay. I think that's enough. You should only keep in mind the example of the free group and the